Alright, so here's a walkthrough of Night Chapter 20 problem set 1, and I tried to not look at these as much as possible, or at least look at what I had done 2 years back, so that this would be kind of like a blind walkthrough so you can see my thought process as I'm approaching the problems. So number 1, a glass rod is charged to positive 5 nanocoulombs by rubbing. First thing I'm thinking is nano is times 10 to the negative 6, and coulomb is the charge. Hopefully that has already been familiar from the notes. So part A, have electrons been removed from the rod or protons added? First of all, protons are in the nucleus, so they can never, ever, ever move. So protons aren't added or removed. And we know that electrons had to have been removed because it became positive, meaning, well, if protons can't move, only the negative electrons can move. If it becomes positive, it loses electrons. If it becomes negative, it gains electrons. So electrons have been removed. And how many electrons have been removed or protons added? Let's get rid of that garbage. So it's important to know that the charge of one electron, which sometimes you'll see represented as E minus, is equal to 1.6 times 10 to the negative 19th coulombs. So if we have 5 times 10 to the negative 6 coulombs, milli, micro, nano. I'm so sorry. This is times 10 to the negative 9th coulombs. I'm sorry that I missed that before. Hopefully when you were starting off with this video, you caught that and you were wondering what the heck I was thinking. So this should be times 10 to the negative 9th coulombs. And we're going to divide that by the charge of one electron, which is 1.6 times 10 to the negative 19th coulombs. And then when we plug that into a calculator, we should find 3.125 times 10 to the 10th coulombs. 4. A plastic rod has been charged to negative 15 nanocoulombs, touches a metal sphere. Afterward, the rod's charge is negative 10 nanocoulombs, so it went from negative 15 to negative 10. It became more positive. What kind of charged particle was transferred between the rod and the sphere? First of all, it's always electrons. So electrons, and in which direction? So with these, I really strongly recommend drawing a diagram. That helps. Plastic charge, it had negative 15 before, and I'm actually going to draw an after diagram as well. I think that has a lot of value. Negative 10 nanocoulombs. This is before, this is after. And which direction? Well, if it became more positive, then electrons went from the rod to the sphere. Now, how many charged particles were transferred? Well, the difference between them, we've gone from 15 to 10, so the difference between them is 5 nanocoulombs, which is the same as 5 times 10 to the negative 9th coulombs. And we're going to do the same thing as we did before. We're going to divide by the number of electrons and calculate how many electrons that is. And wouldn't you know it, it's the exact same problem as before. It's the exact same math as before. It just looks a little bit different. So if the difference is 5 nanocoulombs, it's still going, or the change in charge is going to be 5 nanocoulombs. It's going to be the same number of electrons to make up 5 nanocoulombs no matter how you count it. Two identical spheres A and B are connected by a metal rod. Both are initially neutral. Neutral is a very key term, and this is metal, metal, metal. It's very important to pay attention to whether the rod is conductive or non-conductive. So if it's neutral, I'm going to draw 3 protons. In fact, I'm going to do 4, because 4 is easy to see. And 4 electrons, right? 4, 4. The protons will never move. In fact, I should evenly distribute these on the sphere. So let's put 1, 2, 3, 4, 1, 2, 3, 4. The protons, because they never move, the only thing that can move are the electrons, either to the left or to the right. And that could also either be on a single sphere or from one sphere to the other through the metal rod. Both are initially neutral. 1 times 10 to the 12th electrons are added to the sphere A, and then the connecting rod is removed. Afterward, what are the charge of A and B? So we've added 1 times 10 to the negative 12th, or 1 times 10 to the 12th electrons to this, and because electrons want to spread out evenly and get as far away from each other as possible, if these are both equally neutral, that means the electrons are going to completely spread. They're not going to be more repelled by B or more repelled by A. They're just going to want to get as far away from each other as possible, which means half of them are going to go on to sphere A and half of them are going to go on to sphere B, which means 0.5 times 10 to the 12th electrons, which I'm going to represent with E minus, are on each sphere. And we know that the charge of one electron is equal to 1.6 times 10 to the negative 16th coulombs. Yikes. And we can math that out and find that the total charge on each sphere should be equal to 8 times 10 to the negative 8th coulombs. So now moving on to number 7, 2 identical metal spheres A and B are connected by a plastic rod. Plastic rod is non-conducting, which means no electrons are going to transfer between A and B. Both are initially neutral, and 1.0 times 10 to the 12th electrons are added to sphere A, and the connecting rod is removed. Afterward, what are the charge of A and B? So A, B, I don't even have to draw the original electrons and protons because I've already kind of understood what this problem is doing. This is plastic, which means no electrons are going to transfer. And we have 1.0 times 10 to the 12th electrons being added to this. And they're allowed to fester, but of course none of them will transfer because it's a plastic rod, which means we're still going to end up with 1.0 times 10 to the 12th electrons. So I know from number 6, well, it's just going to be twice as many. So you could do the same calculation before and plug in 1 times 10 to the 12th, or you could realize, okay, just multiplying this by 2 is going to end up multiplying our answer by 2. So you're going to get 16 times 10 to the negative 8th, or 1.6 times 10 to the negative 7th coulombs are going to be on A. And they said on each, or did they just say on charge A and charge B? Afterward, what are the charge of A and B? Well, B didn't gain or lose any, and it was initially neutral. That's important. I should have highlighted that before, but I didn't. So that's still going to be neutral. So its charge is going to equal 0. The charge of B is going to equal 0. The charge of A is going to be 1.6 times 10 to the negative 7. So now jumping to number 9, 2 1 kilogram masses are 1 meter apart on a frictionless table. Each has 1 microcoulomb of charge. So 1 kilogram, 1 meter apart. Each has 1 microcoulomb, milli, micro, so micro coulomb equals 1 times 10 to the negative 6. And I probably should have done this before, but King Henry died belly up, drinking chocolate milk, kill a hectadeca base unit deci centi milli. This is times 10 to the 0, 10 to the negative 1, 2, 3, 10 to the positive 1, 2, 3. Really, These in-between ones are kind of useless. We use centimeters because they are close to inches and it kind of makes sense to use them. But really, the big ones are the threes. So after milli, they stopped doing those in-between ones because it's a waste of time. So if you can remember milli, micro, nano, and then if you wanted to go further, pico and femto, and then I think atta is after that, but I've never once seen atta used. I don't even know if anybody really does use it. But you're still going to follow the same trend. 10 to the 0, 10 to the negative 3, 10 to the negative 6, 10 to the negative 9, 12, 15. And the other, we could go the other way. Those of you who are into computers might say, okay, kilobyte, megabyte, gigabyte, petabyte. I don't know, terabyte and then petabyte, excuse me. Megabyte, gigabyte, terabyte, petabyte. But 10 to the 6, 10 to the 9, it's always about 1,000. Kilo is 1,000. 1,000 thousands are a million. So 1,000, million, billion, 1,000th, 1,000,000th, 1,000,000,000th. It's all about threes. It's all about thousands. So coming back, we now know 1 microcoulomb is 1 times 10 to the negative 6. We have two 1 kilogram masses, so 1 kg. And they're 1 meter apart. And they each have 1 microcoulomb, or 1 times 10 to the negative 6 coulombs of charge initially. What is the magnitude of the electric force on one of the masses? So now we need to bring in that Coulomb's law equation, where the force is equal to k q1 q2 over r squared. The electric force is k q1 q2 over r squared, where k is the Coulomb's law constant, I believe. I'll look that up in just one second. Q1 and Q2 are the charges of the two objects, either pulling or repelling each other. This is one of those situations where you kind of want to use absolute values and pay attention to whether the force is repelling or attracting. Because they're both positive, we know they're both going to repel each other. So the electric force on object A is going to be on the left, and that's the electric force of B on A. The electric force of A on B is going to be to the right. And we can use that to find the electric force. Oh yeah, and R is the distance between them, the radius. So I'm going to have to look up the Coulomb's law constant, and then I'll be right back. That is the one constant I am ashamed to have forgotten. It's 9 times 10 to the 9th, or 99. It's the easiest one to remember, and yet still forget it. So now plugging that into a calculator will yield our final answer if we plug all of our values in to find that the value of either electric force of either on the other would be 9 times 10 to the negative 3 coulombs. So that is the electric force either of B on A and also of A on B. So now we need to know what is the initial acceleration of each mass if they are released and allowed to move. First of all, we need to realize that we need to consider the fact that it is on a frictionless table. If there was any friction, these would never, ever, 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 ever move. Oh my goodness! I hope you caught that, but force is not in coulombs, that's in newtons. So the electric force is in newtons. So now we look at the forces. So I'm going to draw a free body diagram of object A. On a frictionless table, we have normal force up. We have the force of gravity down. And we have the electric force of B on A left. There is no friction, so there's no other force. Vertical forces and horizontal forces are completely independent, and the vertical forces are balanced. It's not accelerating up or down. It's not accelerating vertically, so the net force has to be 0 vertically, or the forces are balanced vertically, which means the only unbalanced force is the electric force. and the horizontal forces. So now we're going to plug it into our net force equation, and net force is just fancy for all of the forces added together, but you can only treat horizontal and vertical. You can only do one of them at a time. So because we know vertical doesn't matter in this problem, we're only going to be looking at the horizontal forces, and that's equal to mass times the horizontal acceleration. And this is the exact same as saying the net force is mass times acceleration, except I'm focusing on the fact that it is horizontal. So the net force is 9 times 10 to the negative 3, and that's to the left, so I am going to make it negative just so I don't forget when I get my final answer. That's equal to 1 kilogram times the acceleration, which we're trying to solve for. And dividing 1 from both sides means that our horizontal acceleration is going to be negative 9 times 10 to the negative 3 meters per second every second. Or it's going to get negative 9 times 10 to the negative 3 meters per second faster every second sitting on this completely frictionless table. And I say it like that because it does not exist. So now jumping into number 10, we have two small plastic spheres, meaning non-conductive, with a mass of 2 grams. And my first thought is, okay, I'm going to have to convert that unit to kilograms so that acceleration and force are in the correct units. And a charge of 50 nanocoulombs, I'm going to have to convert that to, are placed 2 centimeters apart. That needs to be in meters. Always meters, always kilograms, always coulombs. What's the magnitude of the electric force between the spheres? So first I'm going to draw a diagram. Whoops. And we have to go from, I guess we don't even need to look at the mass yet. And I'm pretty sure I only required A for this question, but I'm going to walk through B as well. So we have object A, we have object B, and I'm going to change color because I'm kind of getting bored of this. Let's go with blue, 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 blue. So we have negative 50 nanocoulombs on each one, negative 50 nanocoulombs, or negative 50 times 10 to the negative 9th coulombs. So then we're going to plug it into that same equation. The electric force of B on A and equal to the electric force of A on B, of course, because every action has equal and opposite reaction force. Is equal to the Coulomb's law equation, K Q1 Q2 over R squared. And again, I'm going to put that in absolute values because the signage really, for me, is more confusing than just looking at it intuitively. We know the electric force is to the left. So then plugging in numbers, we can calculate, oh, wait, we have to find the radius. 2 centimeters apart, centi means 1/100th, or times 10 to the negative 2. So that would be 0.02 or 2 times 10 to the negative 2 meters. Same thing. So let's put that in there. That's our radius. Now plugging these values in, we can calculate to find that the electric force is equal to 0.05625 newtons. And now I'm going to look at part B, which wasn't required, but I'm going to go through it anyway. By what factor? And they could have also said what ratio. They mean the same thing. That's kind of why I'm working through this problem, as I think it has value. By what factor is the electric force on the sphere larger than its weight? So what is the ratio of the electric force to the weight? And for this, the trick is knowing that weight is just a synonym for the force of gravity. And your equation for that is mass times gravity. Well, we know the mass is 2 grams, which that's the same as 2 times 10 to the negative 3rd kilograms, because keep in mind, we discussed before, everything has to be in kilograms. So 2 times 10 to the negative 3rd, or 0.002 kilograms. 0.002 times 10 to the negative third, or 0.002, or 2 times 10 to the negative third times gravity, which is 10 meters per second on Earth. And we multiply those out to find that the weight of the plastic sphere is 0.02 newtons. So now dividing these out, we have 0.05625 newtons divided by 0.02 newtons. Newton's going to cancel. Great, we're going to be left with a pure number, which we should be because it's a ratio, it's a factor, it's a fraction. It should just be a number. So dividing that out, we're going to find that the ratio is 2.81, no unit. That's tough in my head still. 2.81 units, or times larger. The big takeaway I want you to get from that is the electric force on scale is stronger than the force of gravity, especially when you have two electrons pulling or repelling each other. All right, number 11. We have a small plastic sphere with a charge of -5 nanocoulombs near another small plastic sphere with another charge. The spheres repel each other because they're both negative. With force, they give us the force this time, the two different charges, and we need to find radius. So you can do this two different ways. You're always going to start with your base equation. And you can either plug all of the numbers in and then solve for your unknown, or the way I like to do it is rearrange for the unknown. So we're going to multiply both sides by r squared so we can get it out of the denominator. Whatever you do to one side, you have to do to the other. And then to get r squared by itself, we're going to divide by both sides by fe. So those are going to cancel out. And then we're going to find that r squared equals k q1 q2 over fe. You could have also cross-multiplied to get the same result. But we don't want r squared. So we take the square root of both sides, and then we'll find that the equation becomes the radius is equal to k q1 q2 over fe. Or rather, the distance between them is proportional to the product of their charges. It's inversely proportional to the electric force, which makes sense. Bigger electric force would mean the radius is smaller. So now we can plug in our numbers and calculate our final answer of 0.0257 meters, or 2.57 centimeters. All right, looking at number 14, what's the magnitude and direction of the electric force on charge A? So this one we have two objects, B acting on A and C acting on A. So the first thing I'm going to do is think about it conceptually. Okay, B and A are negative and positive, which means it's attracting. So the electric force of B on A is going to be towards the right. C and A are both positive, which means they're going to be repelling. So C on A is going to be towards the left. So I am going to have a positive force to the right, a negative force to the left. Keep in mind, I'm going to do absolute values with all calculations as I'm working through this. So using the same Coulomb's law equation for each of these forces, each of these forces, I am going to calculate the electric force and then plug that into my net force equation. And then I'll bring you back after I calculate both electric forces. And now that I've calculated both forces, here and here, the force of B on A and the force of C on A, we found that their magnitudes are exactly the same. First we have to answer, we have to calculate the total electric force on charge A. But we can examine why they came out to be the same. So if we look at B on A, we have 1 Newton on 1 Newton at a distance of 1. So 1 times 1 over 1 squared, because the radius gets squared. But if we look at C on A, and by the way, I was kind of walking through the Coulomb's law equation. Whoops. Q1, Q2 over R squared, 1, 1, 1. But going to situation B, if we look at the electric force of C on A, we have 4 times charge 2. And we've doubled the radius, but that doubling gets squared. So we have 4 times divided by 4 times, and it's going to cancel out, and you're going to be left with a net force of 0 because those two forces are ultimately going to balance each other out. All right, final problem, number 15. Charge Q2 experiences no net electric force. What is the charge of Q1? So we're going to be doing the exact same problem, except realizing that all forces on charge 1 are going to be equal to each other. Oh no, wait, on charge 2. Charge 2 has no forces acting on it. So we need to first examine the forces on charge 2. So first of all, we're trying to figure out what charge 1 is. If this is negative and Q2 experiences no net electrical force, what we found from the last problem, this one's going to have a larger charge value at twice the distance, right? So we could look at this conceptually and very quickly think our way through it. That's actually the right idea. This is going to have to be opposite in charge, because let's say that this is also negative. That means these two are going to repel each other. That means this would have to be positive to compensate for it. Or rather, charge 1 would have to be positive to compensate for it and pull it back. So if charge 2 is negative, charge 1, or let's call this charge C. Charge C is going to repel it, so charge 1 is going to have to pull it back. If charge 2 is positive, then charge C is going to be pulling it, which means charge 1 is going to have to be repelling it. So we already know that charge 1 has to be positive to compensate. Okay, well that's super simple. We also know that the radius doubled. Well, 2 times the radius, if we look at our electrostatic, our Coulomb's law equation, Q1, Q2 over R squared, we know that the two forces are going to be equal. The force of C on 2 and the force of 1 on 2 are going to be equal in magnitude, which means if the radius is getting doubled, keep in mind that gets squared, that means that we're increasing the denominator by a magnitude of 4 times, which means we're going to have to increase the numerator of a magnitude by 4 times. So we're going to have to quadruple whatever charge is pushing or pulling on whatever, that should be on Q2, or Q1, excuse me. We're going to have to be quadrupling charge 1. So if this is negative 2 nanocoulombs, we have to make it positive, and we have to multiply it by 4 to compensate for the doubling of the radius, because the doubling of the radius gets squared to make it 4 times. So we've increased the denominator by 4 times, so we have to increase the numerator by 4 times, so it becomes positive 8 nanocoulombs. You might not have followed number 15 the first time I walked through it, but please, 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 that's why I make a video. Watch it a second time, try to follow my thought process, and then watch it a third time. If that doesn't work, make up any value for charge 2. Call it 1 nanocoulomb to make your math super easy. In fact, you could even call it 1 coulomb, so that way you don't even have to mess with the times 10 to the negative 9s. Make this easy for yourself. And then after you've worked through the math, the same math we did in 14 to figure out, okay, what would charge 1 have to be to compensate for that, assuming we're using 1 coulomb or 1 nanocoulomb. After you've worked through the math and proven it mathematically, then come back and look what I did here about how the radius, increasing the denominator by 4 times would mean we would have to increase the numerator by 4 times. All right, I hope this video helps. Please let me know if you have any questions. Those of you who made it to the end, thank you. I hope you got something out of it. Bye.